How are we doing? Good? Yeah? pH, that's a simple one. I mean, it's not very precise. It's a lot of granularity to that. But. Hey everybody, Owen is starting a discussion that we all need to have together about when is exam 3. Owen, louder for everybody, please.
I think it makes more sense to do it a week after that, because then you have more time to prepare for exam 3,
and less time to prepare for exam 4.
Yeah, the final exam is supposed to be either.
Now wait, hold on, 2 things. There is an exam 4 and there is also a final. Thermochemistry and electrochemistry. Okay, so exam 4 is going to be, do you remember the enthalpy stuff, the delta H stuff from Chem 1? Okay, now we're going to staple a new thing to it called delta S, and staple together and call it delta G, and get a little more deep into that. That's 2 lectures I have planned for that. Then we have 2 lectures planned for the doing redox in Chem 1. Right, with the electron transfer stuff. Okay, I've got 2 lectures planned for that, because now we got to get a little deeper into voltage. Yes, we actually need to do that. So, choose your poison here. What do we want to move quick? So, we do have a 29th of April last day of classes. That's a Monday, and we do have class that day, so that could be our review day for the fun, if you want. Okay? We can move exam 4 down. Where would you like exam 4? You want to move it to 24 April to just discuss things? Okay, we'll do that. Then so I got electrode 2 here and electrode 1. Well, let me do this because I was telling her earlier, I can plan 2 lectures, we never get done with 2, right? So there's that. And then thermo 1, thermo 2. Okay. So, well, that puts exam 3 either Monday or Wednesday, right? That's first is next week, is that right? I think it is. Yes. Okay. All right. So first or third, or put it here, and that's still this day, or this review day one. Choices. Oh, you were advocating for April 8th for the exam. So our choices are first, third, or 8th.
I was thinking about 8th, I thought that example.
What are the average grades for exam 3?
I don't have that ready recall. That's a good question.
They go bad. Last week.
People consider the thermo and electro the harder stuff, I think. Yeah. The redox stuff particularly.
I can add on that. So with the acid-base equilibrium that we're doing right now, it's a lot very similar to what we've been doing with ice tables. Y'all agree with that?
Yeah.
Like we've been doing ice tables for a while. We know how to do that. We're very comfortable with that. Now it's just how to handle that with weak versus strong acid base, right? And calculating pH, pH based on that. So it's actually not much different, just maybe a couple extra steps and some conceptual stuff that's a little different. However, if you're thinking about electrochemistry and thermodynamics, if you think back on Chem 1 and you're like, you had issues with enthalpy and stuff like that, you might want some more time. Because that one is generally harder, in my opinion, than, so, because this one's repetitive.
And there's still plenty of calculation to cover in that. It's not like that one is less calculation.
Right, and the redox part, if you struggle with that, definitely want more time, because it gets more complex.
It does, and I tend to find that I need to recover some Chem 1 stuff about redox.
I don't think that is like, is it a long lab?
Which one is 11?
Like if we took the test on that Monday, I don't just wait it, like you take a lab right after that, it would be a really exhausting.
So lab 11 takes a while. The KSC thing does. I think it's kind of simplistic. How much salt can you dissolve in water? But it takes a while to pull the water away to sea. That's what that's about.
Yeah, the other thing was the one on Wednesday option, which I guess we can do either way. So really, the best option, if y'all want to have exam review sessions, like basically what I've been doing, where I make additional SI sessions on Monday evenings, y'all, I know a few of y'all tell me y'all don't have to say anything about that, but, you know, after your lab, how I'll do additional sessions like that. I could do that next Monday. You could have it fresh on mine Wednesday, or you could wait a week and I don't know.
You can also come this Thursday. That's always an option too.
Yeah, so, I mean, you have chances to prepare for sure. I mean, it's just what you listen
Yeah.
I think the 1 second is already not balance play out for example, Saturday, they and, you know, some people are gonna have more issue with the exam three materials and trouble with exam four.
Yes. All right. So instead of taking today's class for it entirely, let's wrap it up a little bit unless there's some like other drastic things that need to be said about it. Does anybody need to add more discussion before we? Okay. So then let's do this. You could speak up now or let Allison know if you don't want to say so out loud, but are there objections to doing this 3-8? That would be 1 week from right now. All right, hearing no objections, that tentatively passes. Okay, so exam 3 is currently scheduled for Wednesday of next week. Say again. Bonus points. What bonus points? I know nothing about these bonus points ideas. You have not been grading this exam class?
Yay!
Okay.
I mean, like, who needs exams anyway? You know what, we take this exam.
I had a class, I had a class 3 falls ago, like, where it's Chem 2000, where I said, all right, let's assume everybody's getting an A for the class, okay? Stop worrying about the grade, let's learn some chemistry. It worked incredibly.
All right.
But the next fall, I did the same thing, and it failed over. So.
You know what, we don't like things.
So I think we should strive to show, particularly on this final exam, which remember, the final exam is not my questions, right? They're ACS style questions. They're multiple choice, kind of like, remember in the course exams from high school, like those questions, except like big boy version, okay? So be ready for those. If you do well on that ACS exam, give a very strong argument to say, you know what, my grade actually should come up because of how well I did on this ACS.
Let's say I don't.
No, let's not say that.
You know what? I got about like 20 points.
You know what? I get 100 on the final exam. I should just get 100.
If you get 100 on the final exam, there is no justification for you not having an A in this class.
Let's say that they're not gonna.
I don't know what the cutoff is, but somewhere, right?
Exam, I think they do.
Usually, yeah, I take this one. You know, I think the exam.
National norms on these exams. This is what they look like.
What's that say?
How many they got, right? So most people, the peak is right in the middle. Yeah, it'll be perfect. But if you were to get all of these, like it would be professional miscarriage of justice for you to not get an A if you got all of these. So.
You know what? That's fine. Yeah.
I'm 70. You know what? I'm getting a 90.
Beautiful. I'd be very happy to see that. I would be very, very happy to see, yes. Yes, that's what we're striving for, right? Yeah. What did you do last time? Mary, do you remember what you did last time? Yeah, it's long. It's long. Okay.
Should we have a time limit on it?
Yeah? Whatever they give us for final exams, which is longer than the people in that graph, guys. But the people in that graph get 90 minutes. But,
That's basically what we get. Each exam.
Yeah, I've always had people questions.
there's plenty of time on most exams. Practice though, as you practice it, it gets easier. I was just reading a thing this morning about let's say folks who are not as economically challenged as some folks in our neighborhoods are getting by on, a lot of schools are going back to the SAT, ACT requirements. Well, if you've got lots and lots of money, you can just go get a doctor to say you have a PhD and you get extended time on SAT and ACT compared to everybody else. Yeah. And all you need is doctors to get extended time on it. I don't know how that works. I don't know that. But. Anyway, all right. So this is Great Mountain Pine again that I keep talking about because it's a really good thing to look at for pH. Some of the minerals that we collected there, seal, chalcopyrite, lazulite is one of the top right. Yeah, it's a really cool place to collect minerals. That's why I go there, not because to try to, find your danger, but just. Okay, so why are things weak acids or strong acids? What makes a thing be a weak acid or a strong acid? That's true, but I want to go to the next step here. What makes some things more readily or less readily release their proton? What do you mean more? What do you mean about the strength of B bind? It's a very good thought. Y'all follow what Murph's saying here. Do you? Say again? Say again.
The strength of bond that connects the H plus to the rest of the molecule.
Example. So this guy. Do I have a red? Yeah. This H right here has a pKa of 4.756. Okay, so it's a weak acid, but it's a pretty, it's a pretty good one. That's acetic acid. It's a pretty good weak acid. It's not like the weakest. This guy, called ethane, and we don't even think of it as an acid usually. Like Alice is probably looking at it like, that's not even an acid, right? Because we don't even think of it as an acid because the pKa to this is like, I don't know, 50 something. Okay, so it just doesn't. The H's just don't fall off of that thing. Does that make sense? Like 10 to the negative 50, right? So 50 zeros, 1. That's essentially 0. None of it falls off, right? Why, as similar as these are, what's going on? Why is this one so much better, so much stronger? And that's, it's still technically a weak acid, but it's so much stronger than it. Why? Hey, what would we call, back from Unit 1, or from Chem1212, what would we call this type of bond here? Hydrogen bond would be between this molecule and another. Okay, we call this, not this, between this hydrogen and another, not this one, because this one, we can't call a hydrogen bond because it's not attached to nitrogen, oxygen, or fluorine. Remember that? Only FON can have bond, right? Okay. Right. But we would call this a specific kind of bond. What kind? Is it a dipole? Is this a dipole? It's not going to be a dipole bond. No. If it's a dipole, but is it a dipole? Is it polar? C and H are close enough electronegativity to each other, we don't even call them a polar bond. We call that a non-polar covalent or a pure covalent bond. Right? That they share their electrons equally. That's a super, super strong bond. Oxygen, though, oxygen is a lot more electronegative than hydrogen. So this would be an extremely polar bond. Most of the electrons are sucked over to the oxygen side, and the hydrogen, having electrons, I can just float away, right? And that's kind of what it does. It just floats away. Okay? Does that make sense? Let's go a little deeper into that. So, binary compound means just a hydrogen with a thing, like a chlorine, or a fluorine, or a whatever, okay? So that is a simple version, and it depends on that bond strength idea and on that electronegativity of the thing. So, if we're just talking about hydrogen attached to a fluorine, or to a fluorine or bromine or an iodine, those fall off very easy, okay? But if it's attached to something this direction, it doesn't, okay? But I gotta caution you here. I tend to think of electronegativity as one of the big drivers of these things, and it doesn't quite here. Okay, there's a little hiccup in trying to make electronegativity the driver. What's our most electronegative thing of the neutral atoms? Fluorine. Good. So you would expect fluorine to be stronger, and it is not. Okay, so we're going to get to that. So the acid strength apparently depends on multiple things, not just electronegativity. So this gets to a little bit of physical chemistry right here, and the way orbitals overlap each other. Hopefully you saw a little bit of this in Chem 1 with the idea of those orbital overlaps and sigma bonds, pi bonds, and all those, right? Well, how good that overlap is matters. Okay? Now, What are the atomic orbitals on hydrogen? Like if I just here's a hydrogen in Gen 1, probably exam 2-ish. And Gen 1, I don't remember when that was, but what's the electron configuration of hydrogen?
So, 1s, isn't it?
1s1. Yeah. Okay. All right, cool. So what is that first one, what does it mean?
It's the,
A lot of people like to think of the Bohr model with the shells.
yeah,
So what does the one mean there?
it just has one shell.
Yeah, it's just got one shell. It's lit, right? Okay, what would be the electron configuration for, let's go easy first. Let's go with helium. What's it?
It's 1s2.
1s2, so it still just has the one, it's just now 4, right? Okay, how about for fluorine? What's it gonna be? It's gonna have the 1s2 and then 2s2, 2p, 1, 2, 3, 4, 5. 2p5. Remember all that? 2p1, right? Okay, so let's see. That 1s is really small, right? The 2s is bigger and 2p, right? Could overlap with some 2s are bigger than 1s. But 3s are a lot bigger. 4s ginormous. That's why the overlap is 4 for these guys. Does that make sense? Yeah, they're further apart. It's a really good way to look at it. Let's look at hydrogen. And here's my 1s, right? And then fluorine has got 2s1, right? And then it's got your 2s2, right? And then there would be those in each dimension, right? There would be some coming out this way, right? X, Y, and Z dimensions. And so you would get this guy would overlap this one. Does that make sense? But we did the hydrogen with chlorine. Well, it's got all these, but then it's also got 3. Even though, so the red guy doesn't match as well, right? Even though it could be completely enveloped by, it just doesn't match. That's what we mean by 4 overlap. The overlap of this one is better. Okay? The overlap of this one is really 4. Chlorine just takes the electrons, just ignores hydrogen, and hydrogen falls off. And so you have, what do you have here? What would we call this compound in lab? Hydrochloric acid. A very strong acid. Because the match is really 4, and the hydrogen just falls off so easily. This we would call HF, hydrofluoric acid, right? Which is a really nasty compound to get on you, but technically it's a weaker acid than HCl. If we had HBr, hydrobromic acid, it's actually a stronger acid even than hydrochloric. Just never see it. Make sense? So what you get is this trend right here. So as you go across the table here, now this part makes sense. As you're going across the table this way, your electronegativity is increasing, and that's making it a stronger acid. The part that's a hiccup that doesn't make as much sense is instead of strength of acid increasing going up to chlorine, it's backwards. Strength of the acid increasing going down the table instead. The reason for that is that overlap. Okay? And you can see it in the numbers here. Look at your KH. Well, HCl, we don't even usually hang a number on this, right? Because it's an extremely strong acid. But if we go right next door to it, look at that. So the Ka is 9.5 times 10 to the negative 8 for H2S, dihydrogen sulfide. Or right above it for HF, the Ka is 6.8 times 10 to the negative 4. So 10 to the negative 4, technically it's still a weak acid, okay? Does that make sense? But then if you go another step, you get to water. What's the Ka for water? What is it? When do you next up? Yeah. Yeah. So you can see the trend there, right? And then look at that. Cool. So E-10 for ammonia. E-neg little bitty for this guy. This is the Ka, right? So the Ka is the inverse of that. All right. Like 50 for that. Okay. That makes sense? Or if we step in and we look at it, now E is not an element, okay? It's just talking about the electronegativity of element E. All right, and so we're going to talk about bond A being between the element before an oxygen and bond B being the element from the oxygen to the hydrogen. If E has a lower electronegativity, something like, I don't know, iron or calcium or something like that, then let's see, if we had it calcium. So let's make this element, let's see. What are, if E there is a Ca, if it's calcium, right? Then we have calcium bonded to oxygen bonded to hydrogen. What have we just made? Yes. And that tends to be very basic. See that? Calcium hydroxide, strong base. Well, actually, calcium hydroxide. Sodium hydroxide at least is a strong base. Calcium hydroxide does some weird things. Okay? But we can, for Gen Chem 1 or Gen Chem 2, we can call it a strong base, although it does weird things. Come on, right? Okay. All right, let's go the other direction. Let's make E a high electronegativity. What would be something with a high electronegativity? Let's see. How about a nitrogen? Nitrogen's got a pretty high electronegativity, right? Yeah. Okay. So if we bond that to it, NO and H, that tends to help oxygen pull electrons out of that hydrogen bond, or should not call it a hydrogen bond, out of that bond to hydrogen, right? And lets that hydrogen fall off pretty easy. That makes sense? Giving us an acidic component. And if it's medium, like aluminum or something like that, then it tends to be medium. Or carbon. Carbon's a good example. The carbon I had up there a while ago, right? It doesn't help. Okay. Depends on the arrangement. Here, if it's high electronegativity, it's working with the oxygen to pull electrons away from the hydrogen, making it stronger. That's right. It depends on how those bonds are arranged. I think the simpler answer would be yes, stronger. Okay. I don't want to spend a whole lot of time on this. Also, this is, I think this is their textbook. This is the example that it gives in there. And these are inorganic complexes that I don't think they can access this. Right? See H2O as ligand. Let's just put it on there. Shall we? All right. You are still asking about some stuff with the homework stuff, right? And, well, let's do one more thing here so that I can sync back to your question about the homework, because we need to do a stoichiometry piece to do that. And then I think we will extend that homework to give you more time to work on, okay? Okay. So, y'all remember when I put these up, maybe it was last Wednesday, was it? Where I gave you a certain molarity of HCl, and we figured out a pH here, and we got a pH 2. The same concentration, same molarity, right, of acetic acid, and we figured out a much different pH. Y'all still have that stuff? Okay. Now, why is this so different here? Why is that pH 3.5 instead of 2? Because it's a weak acid, and because in doing it, because it's a weak acid, I've got to get an ice table involved. Over here, I didn't need to, I could just assume all of it broke up. Over here, it does not because it's weak. So this is the difference in having to not use an ice table, or getting to not use an ice table, versus having to use an ice table here. Kira, is that okay? All right, time to read your face. Okay? All right. Okay, so you see what I'm doing so far. All right. Maybe I mentioned, not positive if I did, the idea of we make some assumptions. Let me get, for instance, we assume that there's no H plus. All right? Would it change anything if we made an assumption that there's H plus? I don't know, would it? And when does it matter? When does it matter to check your assumptions? All right, let's try it. This might look like a homework question, right? Okay, cool. So this might make the homework easier to do when I read extended here because of working through like this. All right, how are we going to do this question? Read it first, because some of the struggle. Read the text and figure out what's going on. So what's going on in my problem? Carol, what do you see? I agree. So you know me, I'm going to draw it. Right, okay, so keep going. Got some mills. That's where our reactions to the test place are. Okay. Polar, yeah, that's concentration of acetic acid, weak acid, HA, you don't care what the A part is.
And then you add, 1 milliliters.
Oh, no, wait a minute, does that complicate things adding that? Why? What is that sodium hydroxide? What is that? Sodium hydroxide. Y'all know that one? That is a strong base. Oh, well, what's going to probably happen with a strong base with our acid? True that. What else? How? What's the reaction that's going to take place? The OH grabs the H, like what? HOH, more commonly known as H2O, right? Okay. How much? Well, let's start our problem first. Let's start it and see where we can get. Okay, so I'm going to draw. Here's my beaker. How much do we have in there? 100 mils, right? Alright. Now, Kara said we were gonna add some acid, right? How much acid are we adding? When I can't tell you that this is always gonna be true, but I wish it were. When I say how much, I'm asking for what units? Ohms. So how much acid am I going to add? And how do we figure it out? Yeah, tell me what you mean.
So, his molar is moles in a liter.
Okay, so I've got 12 moles per 1 liter, that's 12 molar, right?
And they're 1.3 milliliters to liters.
Yeah, okay, and do what with it? Because I want to get just a mole, so where does what do I probably need to do with my liters?
You're gonna have to cancel off the liters.
Okay, so where does it need to go?
1.3.
Milliliters, but we'll convert it in a minute. So where do I put it up? Do I put it like this? Or do I put it like this? One on top.
So
Okay, all right. Now, one trick, just to make y'all faster, is milli means what? Convert. Okay? You multiply? 0 dot what?
0.0156.
1, 5, 6. Like that?
0.0.
Oh, I got it. I need another 0. Okay, you. So far, so good? Yeah? And that's going to go, that's going to get thrown in. Right? Agree? Oh, okay. Do we need to do this again? Yes. Also put a base. So what am I putting in there? What would you write here in this parentheses? Yeah, 10 moles per liter, right? And what do we get? Agree with that? Yeah? Hey, wait a minute, Carson. What are those gonna do? Alright, so how much of the OH is going to react? All of it. Oh, well then, if that's true, what happens then? How much HA do I have left? One. Ooh. Who is it? One here, you're right, so don't back off. Okay, stick to your guns here because you're right. Okay, now explain.
OH on so equivalent to that, your acid will also use that same amount. Whatever's remaining is
So how much is remaining?
0.0056.
But when you used it up, where did it go? Part of it did, the H part did, but not the A part. See that? And does that make sense? You're right that the H combines with the OH to make water, but that leaves the A minus. Does that make some sense? It's going to become a counter ion in this case. We're taking on the idea of buffers. Okay. Make sense so far? Mercy, that makes sense. Now, so far, you probably don't know why I give a damn about what happened to the A part, but we're going to. Now, Carson, if I have a weak acid system, what do I need to work these problems? An ice table. What's my ice table going to look like? I'll make it easier, AJ.
Was.
The NaOH, we did reaction, all the reaction.
So it showed A minus.
Right? Now, what would we naturally like to do? We would naturally like to say, well, we've got
So did we get, 0.01 mole extra water from that?
So if we take these moles right here, 0.0056 moles HA in 0.1 liters, right? 0.1 liters here? 100 milliliters, 0.1 liters, okay. Then I would have 0.056 molar HA. Because we need molar for the table, right? You agree we need molar for the table for ice tables?
Not base, like, instead of 100 milliliters, it'd be 102.
You could, yes, absolutely. I'm gonna gloss over that, but yes, that would be even better. Yes. It really should be, what are we at, 102.3? Okay. Murph, for upper level chemistry, can I guarantee that? Okay. If you add 10 milliliters of pure alcohol to 10 milliliters of water, it will not make 20 milliliters. It'll make about 16 and a half milliliters. Okay, but you don't care about that right now. Okay, yeah. Okay, so 0.056 molar HA if we ignore the more precise. Do you agree? So if I put that here, right? I'm hoping you want to do the ice tables by now. I can go a little rapidly. Right? And so now I've got, did I give you the Ka on this? We use acetic acid so much, I hope that you know the Ka by now. But if you don't, mercy, if you're working on the exam and I forgot to give you the Ka, what should you do? Yes, please, because I do forget sometimes. Okay, because I do some of these acids so much that I forget that not everybody has that in their head. Okay, so do that. Never hurts to ask. I might not tell you what you want, but it never hurts to ask. So what do I do with that, Miriam? It's a PK. What do I do with it? All right, so I have 10 to the negative 4.756. Why do I want to do that? So I can do what? Equals. So A squared over, like that? Yes? and solve for X, right?
We have another data.
You're absolutely right. You should. And I'm going to show that it doesn't work if we get Jordan. If you do this right here, right now, making a bad assumption that Carson just pointed out, right? We're going to get a pH of 3.99. That's not correct. Everybody see where I'm at on that? Yes, go ahead.
So we're gonna have the equation where that assumption is wrong.
Yes.
Okay. I want to know because I cannot likely get on the phone. I don't know.
Yeah, what is work on a calculator?
Like anything to do with quadratic formula, I don't know why.
Have you been to the math lab to practice quadratic formula?
No.
That's my first,
time.
that is my first, thank you, first recommendation, because they're gonna probably be better at practicing with you than I am. I really think you should like sometimes certain math classes you take, when you get ready to take out two, right? Just bring a sleeping bag to the math lab, because, okay? So, all right. You're the problem. Like, why are you bringing a sleeping bag to talk to? Oh, okay. All right. Yeah. Okay. So, let's see. Let's bring this back down. Now, I did do this already. I already animated this. I just wanted to set us up so you can follow. Sometimes when I just animate it, it might not be as easy to follow. So, y'all slow me down when you need to, okay? So, this is what we were doing here. We calculated, right? And Miriam said we could just subtract those, right? Giving that many moles of HA. And then we'll do an ice table, okay? So I'm going to do it 3 different ways. Okay, so let's see. Orange one first. Ignore those others. They don't exist yet. This is the one that we have set up right here behind the screen, right? Let's see, and we solve for X. Take a negative log of that, and we get a pH of 3. It's way, way off. Okay? Does that make sense? Carson, talk me into the green way now. Why would you say we need to do it the green way instead of the orange way? Looking up there, see what I did differently? It's what you said. So tell everybody why you would advocate to do the green way.
Because after the acetic acid and AOH reacted, there was still some of the conjugating acid left over.
Conjugate system. Right? And so you should do what with it?
Yes.
Oh, well, now let's see. It's also in 100 mils, so 0.01 moles, A minus N, 0.1-ish, liters, right, is 0.1 molar, right? You see what I did with my 0.1 molar for the green, the middle one? Yes? So far, so good? Everybody process the green. We're ignoring the purple. Purple doesn't exist. Okay, so the orange one is the first version, but now the green one is Carson's version where he's like, look, don't ignore the A. A's there, right? Does that make sense? And look how different. Look at my pH. And you got to remember, y'all, pH is like earthquake scale. It's logarithmic, right? So a magnitude 5 earthquake is not a little stronger than a magnitude 3 earthquake, right? It's 100 times stronger. Does that make sense? So pH 5 is 100 times different from pH 3. Very, very different. Does that make sense? See that? See where it is? Yes.
What is the subset on it?
That it is not a significant figure, but I didn't want to lose it.
Okay.
Okay, yeah, there are only three significant figures. But the next figure, if you want to see it, was a 7. So that's,
Yeah, just did it.
okay. Good? Well, we're gonna talk about that, Lori. So, let's see. Now, it turns out, we actually made another assumption. This beaker full of water right here, did it have any H pluses in it? It's water. Does it have any H pluses to start with? How much? Guess what? 10 to the negative 7, right? It had some H plus to start with. 1 times 10 to the negative 7 H pluses. Oh God, we made another assumption. In fact, we made a lot of assumptions that I've not even begun to talk about yet. Okay? But the purple one, fine, I'll put that one in. So now I put in an initial value for the H plus of 1E-7. But what do you notice about the green answer versus the purple? Somewhere our assumptions stop mattering. Does that make sense? And so this assumption threw us way off. This one did not. Okay? Sometimes it will. Sometimes you may need to go put this one back in too. Makes the math a hell of a lot harder. Okay? Because now you've got, on top, instead of x squared, you've got 0.1 minus x times 1e-7 minus x, right? So you've already got a quadratic on top of a binomial equals a constant. Oh God, right? That does make the math harder. That's why you make your simplifying assumptions to make your math easier. Okay? Does this make sense what I've done? Yes.
So if it was on an exam, would you want us to check both of them?
Yes. But what if I gave you another way, a nice equation way to check? Would that be nice?
Yes.
Because that's on the next slide. Okay? This next slide has another thing called the Henderson-Hasselbalch equation that we're going to spend some time talking about. Down here is another yet new way to check. Okay? It says, and we're, like I said, don't worry about this, I'm going to have slides for this thing by itself. But you need to take, to find the pH, you take the pKa plus log base 10 of the A minus species concentration over the HA concentration. And I did that here, and I got, which is what we calculated with both the green and the purple. Does that make any sense? In real life, yes. On the exam, please don't. But yes, in real life, yes. So you're a biology major, and I will tell you that I never once saw a biology major do a nice table in lab. Henderson-Hasselbalch all the damn time. Does that make sense? However, when I was presenting to the chemists at UTC, their immediate response to that slide right there was, yeah, Henderson-Hasselbalch equation is crap. So biology versus chemistry, right? You know, okay? So, does that make sense? There you go. You like that bottom one better. Okay, I got you. No, I mean, yes, in a biochemistry lab, you're going to do Henderson-Hasselbalch because the real answer is you do Henderson-Hasselbalch, you mix your buffer, put a pH meter in it, and put some acid or some base in it to adjust it. Okay? All right, ready? Because some of those other assumptions that we haven't even mentioned yet, there are other assumptions. Yep, there are other assumptions. Oh yeah, I found this. Hydrolysis. What is hydrolysis? Yeah. Okay, and the lysis part? Breaking something up, right? But your textbook doesn't have that word. Until chapter 13, where they just start using it as if you should know it. This is one of those gap things. Nobody ever told you about how hydrolysis, and then they're like, yeah, but you sure know what hydrolysis is, so let's go. It's one of those things. It's one of those words that's poorly used, I think, in science, right? We just assume everybody knows what we're talking about. Probably we don't know what we're talking about, so it's becoming more difficult. But it just means you've got water involved in breaking something else down. Okay? So hydrolysis of a protein is you've got water involved in breaking down a protein. Yes.
So for the test, you want us to just go into the ice, then the holding bag, and then do the
How small? Yes.
to check our answer.
There are some other questions that we're going to have in dimensional as well too. Which one? Like I said, there's going to be slides on the endocrinology block coming still. Okay. So, all right, new scenario. New scenario. I'm going to erase this scenario up here. Instead of adding a weak acid, we're going to add something like ammonium chloride to water. Now, ammonium chloride is a salt. We add ammonium chloride to water. Well, cool. That should be all good, right? That should make salt water. pH should still be 7, right? It is not 7. Why would it not be? Why would I claim that the pH is not going to be 7 when I'm just adding the salt? There's no salt in it. Hint, a word you need here is conjugate.
Is it for HCl?
Okay, good. So HCl. So if we had Cl minus, right? That is the conjugate base for an acid, right? What is it, Carson? For this guy, HCl. Y'all agree with that? Yes? Okay, well, ammonium then, let's see. That's ammonium. If the Cl part is the conjugate base of some random acid, what do you predict about ammonium? So I'm saying the Cl is the conjugate base for some random acid, then ammonium is the conjugate acid for some random base. Agreed? Well, let's see if we can figure it out. So a base, let's just think of it as going off of the OHs, right? What does that imply on the other side here? Where did my OH probably come from? Water, so let's do that. What does that mean? NH3. So, chloride is the conjugate base for hydrochloric acid, and ammonium is the conjugate acid for ammonia. Okay. Well then, close your eyes on this. It doesn't exist for a second. If I say, give you this much HCl in water, how much of it breaks up? You'll tell me what? Why? It's correct. Why? Because it's somebody help me. Strong acid. Oh, okay. All right. So, well, Cl is the conjugate base for a strong acid. Therefore, if all of it will break up, now let's go backwards. If I put Cl into the water, how much HCl will it form? Think logically. If I put HCl in water, how much of it stays HCl? So if I put Cl in water, how much HCl forms? None. Well, look, if I put this in water, all of it breaks up, right? If you put this in the water, none of it goes backwards. Does that make sense? Because this is a strong acid.
Oh, yeah.
Yes? Okay. That logic does not apply up top because ammonia is not a strong base. So if I put Cl in water, 0 HCl forms. It all stays Cl. But if I put the ammonia in the water, it's not 0 in H3. It's some amount of NH3 sucking OHs out of the system, right? Causing pH to go down, causing it to become more acidic.
So, equilibrium, what does it make when you add?
Well, the Cl does. Let's look at this. This one does. Because there's an equilibrium. It doesn't matter if, get rid of this guy. If I put 1, 0, 0, plus x, right? Or if I put 0, 1, 0, make sense? Minus x. Whichever one you've got too much of, it's going to make the other. That's what an equilibrium is. That's how that does. The Cl one, all of it stays Cl. This is strong. It is an equilibrium. So you may be thinking a little deeper than we need for Chem level, okay? But HCl is a strong acid in an aqueous system. It technically does have a pKa, right? But it's like negative something like that. I don't know, because nobody ever calculates with it because it's so strong. It's actually stronger than H3O. That makes sense. So there is one, you just don't bother with it because it doesn't have any water. But if you're working in a different solvent, like in orgo, you'll be working in toluene or with a UNSO or some of these other solvents. Does that make sense? All right, y'all? Happy with that? You give the theory behind it, please. Yes? Okay. So the Cl and the NH4, this is what we just did. So you do it in Ka, stay extremely large. Okay. This 1.8 yeah, that we can calculate. What do you need 14 over extremely large is extremely small. I can't put numbers on it if my calculator won't hang. Does this make sense? This that's a number that your calculator can do. Okay? So what is the pH of a 1 molar ammonium chloride solution. How would we approach this? How would we approach it? All right, hold on. What if I say, Kira, do that a bit. Kira, what's the pH of a 1 molar ammonium solution? Could you do that? If I give you the pH? Same question. Makes sense? Okay. It's just that I've given it to you all as NH4 plus instead of NH, but it's the same question. So you just put it in your ice table, right? And run it this way. Make sense? Yes, maybe, maybe. Okay. But Carson, this is the question we have. Make sure this is all formed. That's what you got to look at. So you're going to make a strong acid or base, the conjugate. And how about the other side? They're going to make a strong acid or base conjugate. Okay? So, now you got to look at these. These are neutralizations. Again, this ties to your homework questions, right? Okay. If you got a strong, oh wait, let me ask you, Alice, in general. Actually, no, I want to ask everybody, including Allison, though. Chem 1, do we make titration curves? Did we make a graph and draw a curve for a titration? You remember the titration where you're titrating to get the perfect pink color? You remember this lab? Yes. What did y'all do with it?
Just did titration.
Just look for the pink.
Yeah.
There's no graph.
Okay.
How about my class? Did we do a graph? We did? You think so? Alice? Your thoughts in general sense? Yeah. Where did titration curve show up?
Well, I saw it really like actually builds. I built
Actual line. Okay, great.
because that's where it starts to make more sense.
Yeah.
Because titrations in Chem 1 and Chem 2 for me was finding the concentration of something.
Okay, so we're gonna have to fill in some gaps here, okay? So a titration curve is a graph of, generally, you can do these a bunch of different ways. How would you get line for? Generally, for a pH titration, which is not the only kind of titration, but for a pH titration, generally you're going to plot pH on the y-axis and amount, moles probably, on the x-axis, okay? Could be confusing. Some people might do volume on the x-axis. Some people might do time on the x-axis. So, but there's a reason that he's thinking of a drift, a very constant drift, and then time can be the x-axis. No problem. Just you need to know what he's doing. Okay. All right. So when you're trying to get the perfect pretty peach color before the pink color, remember that for the titration? Okay. That's because your pH is very low to start with. Okay. And then it's gonna have a form like this to very high. Okay? Because you're titrating in sodium hydroxide, which is a strong base, so you're approaching a higher and higher pH as you get. Okay? Does this make sense so far? You ever seen that person? Say again?
I said, I haven't seen it put on a curve.
You have not seen it on a curve. Yeah, okay, so I need to have this discussion with you. Yeah, this is that homework that I thought, it'd be good, it wasn't. I'll extend that for everybody. This is what it's talking about. Okay? So on the titration curve, there are certain points that are really, really important. The first one I want to discuss right here. This is where that perfect peach color happens when you're doing this titration. Because up here, for phenolphthalein, for phenolphthalein, this is pink. This is clear. This is clear, okay? And there is this very, very tiny, now it looks big when you look at it here, right? But remember, what are you putting in? Volume. On the x-axis, this is tiny. You see that? This is why titrations work, because the shape of this curve finds a very tiny volume difference. Differential in volume is very tiny. So this right here is called the equivalence point. And the word comes from when you have had an equivalent number of moles of base to the number of moles of acid that you had to start with. So when you've added an equal moles of titrant to your solution. Does that make sense? So it's an equivalence point. Okay? Yes, so far? Yvette, did you see this in your AP? Y'all did do it as curves? You did not graph it.
Moles of acid and moles of base are the same.
Exactly the point. All right, she called it neutralized. Okay, y'all, that's the point. This is really a neutralization reaction, right? So now I've got 4 cases up here on the screen. Okay, so in the first case, this is the simple one, and this is the one to think about. Everything else in terms of the simple, and we'll complicate it as we go. All right, but the simple version is a strong acid, strong base system. So if you take an HCl solution and you titrate with a sodium hydroxide solution, that's a strong acid and a strong base. The reason nobody does this is because it's boring. Because the equivalent point for a strong acid and a strong base will always be at pH 7. For a strong acid, strong base system, in water at 25 C, if the moon's aligned just right, and if there are no dolphins, anyway, but yes, it'll be a 7, okay? All right, good so far? The simple one just makes a nice curve. pH is very low until it suddenly shoots up, goes through 7 right in the middle, and then tops out very high. Does that make sense? Good? All right, strong acid, strong base. Now, it gets more complicated. Strong acid with a weak base, what's going to happen? Think ahead. I got some slides for it, but think ahead. Then we got the inverse of weak acid with a strong base. What's going to happen? Right, this is the actual one we did in lab. And then there's this horrible situation, which Alice is probably not ever even done, of a weak acid with a weak base. It's terrible. Okay? All right? So you got your predictions in your head for what's going to happen with them? Yes? Owen, have you formed a prediction? I'm not going to ask for that. Have you formed one? Go ahead and form your predictions. This is kind of teacher-ease where you get to predict ahead and then change your misconceptions if there are. Okay. All right, here's the strong acid, strong base. Here's what's happening. Right? So you're titrating along, you're adding 5 mils and 10 mils and 15 mils and 20 mils and 30 mils not overshot. So remember, overshooting is shooting purple. Right? Well, here's what's happening. It's real easy to shoot through that curve. But for strong acid, strong base, pH 7. Right? Good. Good so far. But with a weak acid and a strong base, looking at this curve, does the shape seem pretty similar to the other one? Except what? Now, what do you see? I mean, back up. Get this one in your head. Okay, so Owen says what it is shifted up. The equivalence point is no longer at 7, right? It's where now? Like almost 9, 8 point, right? Does that make sense? All right, look more. What else has changed? What do you mean by squeeze down? This is strong.
Jump from
Yeah, it's made this part of the curve not so sharp. See how that's got more of a slope to it, right? See that? So this tells you this side, the acid side, is not strong. The acid side is weak. The stronger this pK is, the more curvature there will be. Does that make sense? And so the less curvature you have, the weaker your, in this case, acid, because we're down here on the acid side of the pH scale, the weaker your acid is. Look up there. My base is still strong because that's still a nice tight curve on the top part. Does that make sense? Yeah? Okay, Gary, I bet you can guess. You can tell me what a strong acid weak base curve would look like, right? What would you guess?
For strong acid.
Yeah, so this is weak acid, strong base. You're going to guess strong acid, weak base.
So, like, it's gonna be more curves for strong acid,
So stronger curvature here.
and then for weak base, less.
Yeah, does that make sense? Does that make sense? Now? Yeah. That makes sense? Now, don't get confused by the fact that this looks flipped over the other way, because remember, if I've got a weak base in there, right, and the pH is high to start with, and I put down, it's about, it's the shape you care about, not which direction. Okay? Makes sense? Yes? Maybe? Arson? Set it out? About full? Yeah? Weak acid, weak base, like I said, these are horrible. What do you see about this curvature? It ain't great. It's kind of what you see. It ain't great. When you try to do these, you're like, I don't know, was there a change here or not? So you start trying to plot derivatives and yes, it does. Right? Remember yesterday when in quantum we were doing that, and we're supposed to be plotting, I don't know if Carol was plotting the derivatives or not, but you should be plotting the derivatives on that. So that you're looking at where does the inflection point happen, all that kind of stuff. Okay? All the calculus, when you get to calculus and they're like, these are inflection points and they're really, really important, like, dude, they're a an inflection point in my life. They are actually important, I promise. Okay? All right. All right, we have no time to start buffers. So Monday's class will be buffers and Henderson Hasselbach, and Wednesday's class will be anything.
I will go ahead and put in a proposed addition class in our section, which will be that. So what would y'all like to do, like kind of like game oriented stuff, if you would days to work like that.
What do you want for your review?
Yeah. This is the most practice problems of the time we have.
Break up those problems. I've got one.
Do you need some private problems?